So a claim is made that the average amount of sleep an FGC or a student gets per day is less than 8 hours. And I have defined the average to be mu, which is the average amount of sleep an FGC or a student gets per day. Our objective is to verify if we have support toward the claim. We're not going to say that we're accepting the claim. We're going to look at the law and conclude that there is evidence, significant evidence to it. So, the very first step is to identify the null and the alternative. The null must have the equal sign always. So typically we try to find evidence toward the claim. So the claim here is mu less than 8 hours. What is the counter argument for mu less than 8 hours?
More than 8 hours. Greater than or equal to.
If you look in your textbook, the textbook probably uses mu equal to 8 hours.
Which one do you count for?
I go for that, that's formal, but
Okay.
either would work for me, but your textbook goes with mu equals 8. Alpha is 0.05. In other words, the probability of type 1 error under the given law has to be 5% or less. That is the standard that we set. As I mentioned last time, the researcher chooses this value, and it is often subjective. One person might pick 0.1, another 0.01, but the most common value that is used is 0.05. The third step from last time is where we collect a sample, which we did. And we compute sample estimates. So we have to find the sample mean and the sample standard deviation. We know how to find the sample mean and the sample standard deviation given a sample. So go ahead, put that in list 1 and tell me what the mean and standard deviation are.
7.57 and 2.43.
2.43. How many do we have, Fancy?
14.
30?
14.
Turned out to be a nice example. So, you look at those values. The claim is that the average amount of sleep would be less than 8 hours. We collected a sample. A sample is telling us it is 7.57, certainly less than 8, right? Do you think that the claim is true?
Yes.
How many of you think that the claim is true? Do you have a question?
Yeah, it's wrong.
It's wrong? Okay. How many of you think the claim is true?
No, I mean like the numbers up there are.
Oh, the numbers are wrong? Okay.
You're like, okay, moving on.
N should be 16.
Okay. I think you need binoculars, Josie.
The mean is 7.4375.
Okay.
So the standard deviation is S axia.
Mm-hmm.
Okay, that's 2.301.
Could someone verify?
I got
Yeah.
the same numbers.
Okay, where'd you go wrong, Josie? Did you enter?
I forgot the last two.
I think it's because when you put like decimal points, it's like in the middle. And so it's like sometimes confusing to copy it down from the
Ah, I see. Instead of putting it down. Okay, so that's 8.5. So regardless, the point being, you look at 7.4375, which is obviously less than 8 hours. So how many of you think that the claim is true? 1, 2, 3, 4, 5, 10, 12. How many think that the claim is false? In the sense you don't find enough evidence to work for the claim. Just one person? Why not, right? We can't be wrong. I think that the claim, we will not find enough evidence to word the claim. And we're not going to support the claim just by looking at it. The reason being, even though numerically 7.43 is less than 8, from a statistical standpoint, we will not have enough evidence because of the standard deviation, which is 2.30, which means there's a lot of variability involved and we won't have enough evidence to support the claim. We will see. How do we come up with a conclusion? We compute a test statistic. In this case, it is T. X bar minus mu naught divided by S over square root of n. We have seen this formula before, which is in confidence intervals. So that is the standard error. Mu naught is the null value, null or the reference value. And X bar is the sample mean, which is 7.4375. So plug in those numbers. We can't have just 2 decimals. I've rounded to 7.44. And tell me what that number is. Now that we have the test statistic, the last step is to obtain a conclusion. There are 2 ways to obtain a conclusion. The first one is the critical value method. The critical value method is preferred for instructional purposes, so you understand the method, but in practice we prefer the Pvalue method. So how do we do it? First, you've got to identify the rejection region. The rejection region depends on the test that you perform, left, right, or two-tail. If it is a left-tail test, the rejection region would be on the left-hand side. If it is a right-tail test, the rejection region would be on the right-hand side. If it is a two-tail test, the rejection region would be
All over it.
all over it.
Both sides.
Both sides. Now, what do I mean by side? A t-distribution looks very much like a bell curve. That's the real number line, so that's the t line. Oops, sorry. It is a left tail test, so the area has to be on the left-hand side. And on the real number line, that interval is what we call the rejection region. And we have to find that critical value. And how do we find that critical value? We find that critical value by using the value of alpha that we chose at the very beginning. What is the value of alpha? The value of alpha is 0.25. So the notation here is t, because we're using a t-distribution. T sub alpha, comma, n minus 1. N minus 1 is the degrees of freedom, just like the one that we used for confidence intervals. So in our case, it would be t sub 0.05, comma, n is 16, 16 minus 1, 15.
What did you write under one?
df. How do we find that critical value? We can either use the chart or
Inverse t.
inverse t. So inverse t 0.05, comma 15, and what do we get?
Minus 1.753.
It happens to be minus 1.753. So we go back to step 4 and look at the test statistic, and that value happens to be negative 0.97. So get your binoculars ready. So negative 0.97. So the test statistic is right there. The rejection region is any interval below negative 1.753. My question to you is, did the test statistic fall in the rejection region?
No.
No. So you do not reject the null. If you do not reject the null, the claim doesn't have enough evidence. So what's your name? Jose? Wait, what's your name?
Chris.
Chris. So there is no evidence to support mu less than 8, and Chris was correct. Oh, Steve. Because just by looking at this, I can tell whether the null would be rejected or not. But we want a precise answer, which is why we do all of this. Even though the sample mean is 7.4375, is it significantly less from a statistical standpoint for us to conclude that claim? No. Numerically, yes. Statistically, no. Are we clear? Yes.
I have a question.
Go
Is
ahead.
area equal to alpha or alpha over 2?
Alpha. It is a one-sided test. With confidence intervals, it is alpha over 2. So that is a good question. We're using alpha because it is a one-sided test. So if our test is right-tailed or left-tailed, we would use area as alpha. Question?
So if it's two-tailed, we'll use alpha over 2?
Yes.
How do you know whether or not to use like interval T or interval Z? Like how do you tell the difference?
So in this class, we're going to use only T. But in practice, if you know the population standard deviation, you would use the Z-test. If you do not know the population standard deviation, you would use the T.
It has nothing to do with like how many
Nothing to
things
do
are in
with
the sample or anything like that?
No.
Okay.
So for the exams, we only need table A3. We don't need table A2.
Yeah, because I
Like, because in the homework, it had us use like
Z and D, yeah.
You only need the t-table, and you only need the t-table if your calculator doesn't have inverse t.
Yeah, mine does that.
Otherwise, you don't need tables at all, period.
Okay.
But, so when I said a long time ago, the homework system is going to ask you to use the table, but you can avoid that entirely if you understand the concept and how to do it using the calculator. Everything that I did in class pretty much used the calculator, but I did show you how to use the table, but is it effective? No, not these days. I still don't understand why they force you to do it. Okay, so we already know the conclusion, but as I said, critical value method is an approach that people take to explain hypothesis testing, but in practice we rely on something called the Pvalue. So for a left-tail test, the p-value is the area below the test statistic. In other words, it is the probability of the area under the density curve. It is the probability below the test statistic. So how do we find it? Well, we know what the area is. I can use the same graph. Where is the test statistic here? Right there. Okay, got to use a different color. And I would want to find the area below the test statistic, which would mean that. Yes? Look at the picture and tell me, even before we get into the numerical value, do you believe that the p-value is going to be bigger than the 5% or less than 5%? It is going to be bigger than 5% because the area in blue is bigger than the area in black. We're black and blue. Do we know that album? Okay. guys have bad taste in music. So the area in blue is actually bigger than the area in black, so naturally the p-value will be bigger than 0.35. So this is going to be definitely bigger than 0.05. And how do we find the area? We're going to use a CDF function, and if you have to guess, what CDF function would you use? What alphabet did I,
Alpha.
alpha?
T CDF.
I said alphabet, not Greek alphabet. T, right? So we have to use TCDF. Area below the test statistic, so we start at negative E99, go all the way up to negative 0.97, and degrees of freedom, which is 15. And what do we get?
0.1737.
We already agreed that that value will definitely be bigger than 5%. Is 17% bigger than 5%? Yes? Yes. Okay. Not done with the problem yet. Okay. So the p-value is 0.1737. So since p-value is less than the alpha that we chose, sorry, greater than, what am I saying? We do not reject null. If it is less than, then we would. So here, p-value is 0.1737. Alpha is 0.05. Why should that make sense? It goes back to the informal definition that I wrote last time. What is alpha? It is the probability of false positive it is the same as saying the probability of error in rejecting null. There are very technical ways to express this, and I don't want to get into that in a beginner level class. So I went over false positive, which is type 1 error, and it is the same as saying error in rejecting null. At the beginning of the problem, I said that that number has to be 0.05. Yes? So we collected the sample. P-value is the probability of error in rejecting the null based on current evidence. Now that we have observed evidence, what are the chances that I could be wrong, or I could be wrong, if I rejected the null and said, oh, there is support toward the claim? That error probability is 17.37%. Right? Would you want to make a conclusion knowing the fact that there is a 17.37% likelihood that you would be wrong?
No.
Would you? Absolutely not. You may say, well, what if it was 6%? Would you be willing to do it then? If this number were to be 6%? Why not?
Because the values that you gave us last time we had class were 1, 0.5, and 0.01.
So I've set a standard for myself, and that standard is I would like to have 5% or less. That's why I stressed the importance of alpha and how subjective it could become. For me, the standard is it has to be 5% or below. So even if I got 6% here, I'm not convinced because my standard is 5%. So I need to have 5% or below. So that number is 0.25, that's what we set. This is what the data is telling us. So naturally, we should not reject null. Does that make sense? Yes? If you look in the textbook, Pvalue has a very formal definition. This is informal, but informal one is easy to understand. The formal one. So the formal definition that I'm about to write typically is well understood when you reject a null, but I'll just write the definition here and let's see if you like it. How many of you like that formal definition compared to this informal definition? Jesse, why?
It's more obvious that you want something as far, in this case, to the left as you can.
Okay, anyone else? So when we reject the null, the formal definition would make better sense, but to understand something quickly, you can use the informal definition. What does it actually mean? It is a probability of observing a conclusion that is as extreme as the current conclusion. So if I reject it, for example, if a null is rejected with a p-value of 0.0005, I have rejected, that is my conclusion. So what are the chances that I would see such a conclusion that is as extreme as the conclusion of rejecting the null? It is only about 0.05%. Does that make sense? Would you consider this to be a rare occurrence, or did it happen by chance? Would you consider that there is an effect or no effect? That there is an effect. In our case, the probability of observing a conclusion that is as extreme as the current conclusion, well, it's not extreme to begin with, right? Because we did not reject the null. But what are the chances that we could see such a conclusion if we rejected the null by chance, it's about 17.37%. In other words, this is not a rare event. It could happen just by chance, and there is about 17.37% chance for that to happen. So that is the formal definition of p-value. Again, that is best understood if you reject the null. So which is why I used that example. If the null is rejected, and if it had a p-value of 0.0005, and I asked the question, well, what are the chances that I would see such a p-value again? It's only about 0.05%. Very, very small chance. So there is a significant effect from the sample. Does that make sense? Okay. Now this entire process can be completed with a few clicks using your calculator. So grab it if you have it. Okay, so do we have the data entered already? Because I don't.
What is it? Stat.
It is the same thing that we've been doing. Start, edit. Okay, so what I did is I simply entered the data that we have into the calculator. Press start, go over to tests. Option number 2 is ttest. And it is asking you for an option. It is giving you 2. It's asking you to choose one. Should you choose data or statistics only? We have data in this problem, so I'm just going to select data. Mu naught is the claimed value, or the reference value, or the null value, and what is that value in this problem? 8. Now where is the data? The data that I entered is in list 1, so I'm just going to leave it as is. I have 3 options listed over there. Those correspond to the alternatives. So we have mu not equal to mu naught, mu less than mu naught, and mu greater than mu naught. What should we choose? Less than mu naught, because the alternative that we defined at the very beginning is mu less than 8. So that is why I suggested last time that when you write the definition, you've got to be extremely careful, otherwise your entire answer would flip in the other direction and you'll get it wrong. Yes. And hit calculate. What do we say? The first line is t. T is negative 0.9777. That is the test statistic we had earlier, negative 0.97. The p that you see there is the p-value. It's 0.1719 if you round it. Here we have 1737. Why are they different? Why are they different? That value is 0.17185. This is 0.1737. Benton.
Rounding?
Rounding. We rounded a whole lot of things here, especially the test statistic. We rounded it to negative 0.97, which is why that there is a slight difference. I would recommend that you keep up to 4 decimal places in your computations for test statistic and statistics, and p-values up to 6 decimal places before rounding at the very end. The next slide is the mean, which is 7.4375. That's what we had. And the standard deviation is 2.3013. That's what we had. So all I have to do is look at the output that I'm seeing, and I can come to a conclusion right away when I see that. All I need is that p-value. If that p-value is less than the alpha that we set, then you reject the null. If it is greater than the alpha that we set, you do not reject the null. Does that make sense? Instead of calculating, there is another option. Instead of calculate, if I said draw, it is drawing something. Can you tell me what it's drawing? Yeah, but which one? Is it sketching alpha or is it sketching the p-value?
Sketching alpha. No.
It is sketching the p-value. So the shaded area would correspond to the p-value that's listed there, 0.1719. If I were to do a right tail test, what would I change?
The bottom one, you would.
Everything would remain the same. If mu naught changes, we are going to change mu naught. But what should change here?
But you should make it the third option.
Should make it the third option, right? That would be for a right tail test. For a two tail test, it would be the second option. Oh, sorry, first option. Does that make sense? Yes? So you identify the mu naught from the problem, you identify the type of test that you have to perform, and you can do it directly using a calculator. You may ask me, well then, why did we do all this stuff? Because in the homework or on the exam, we may just simply ask you to find t, given x bar mu naught and s or the square root of n. So that in order for you to get to that t value, you've got to know the formula. Are we clear?